Great, thanks for the introduction. Hi everyone, I'm Shanghang Zhang, a postdoc researcher from UC Berkeley. Today I'm very happy to be here to introduce my research on learning with limited labels. So nowadays, deep learning has brought great success to many fields like autonomous driving, speech recognition, like to beat the human players, for the natural language processing. However, there is still a very big issue for the deep learning, which is the data inefficiency. The learning often requires millions of labeled examples. So the models usually need to label the sample set span all the variations. However, it is quite expensive and infeasible for the particular applications like traffic and medical imaging domains. So without this many labeled data, the models fail to generalize well to the new domains or tasks. For example, you can see in these images, so we have the training images which are labeled from the Berlin web cameras. If we train our deep model for the semantic segmentation on such images and test on the same set of images from the Berlin webcam, it performs quite well. However, if we test this trained model on the web camera video from San Francisco, it suffers from very poor performance because the things of the San Francisco traffic can be very different from the Berlin web camera traffic. Especially when there is no tunnels in the Berlin web cameras, and if you test your trained model to the tunnel images in the San Francisco web cameras, it can be even worse. It's almost totally fail. Actually, such domain shift between your training data and testing data widely exists in the real world, like in the transportation, in the medical imaging, and in the industry. We usually have a lot of labeled data on your source data, like these different cameras are labeled with several images with the bounding box of the vehicles. However, we often have a testing target domain that has no labeled data at all. So the problem is how to adapt your deep neural network to the new domains without any labeled data. Such problem calls for the research on domain adaptation. So today, I will introduce a series of research that's dealing with such domain shift problem. I will first introduce our work on adversarial multi-source domain adaptation. As you may see in the previous slides, we have the web cameras in a city, like in this Manhattan area of New York City. You can see that spatially, the cameras from different intersections of the city can have very different background, different camera perspective, even different traffic density. Similarly, in the temporal domain, even for the same camera, it can also have different weathers, illumination, and traffic density. So all these variance brings the requirement for a large amount of labeled data, but it is quite difficult to label this enough training data that cover all these cases. So we want to develop some domain adaptation method that can transfer a model trained on these labeled source images into the unlabeled target images. How to do this? First, let's take a deeper look at the deep neural network. A typical neural network can be understood as two parts. The first one is the feature extractor, and the second stage is a label predictor. So if the input image from source and target are different from each other, we may try to make this extracted feature from the feature extractor to be very similar with each other. So it can be indiscriminated from the source and target domains. However, at the same time, we also want to make this extracted feature to be discriminative for your final prediction task, like traffic counting. To achieve this discriminative feature for your final prediction, we want to have a small risk on your labeled source data. And to achieve this like a small source and target divergence, we want to achieve some high classification loss between the source and target domain classifier. So with such intuition, we develop this adversarial multi-source domain adaptation method. So let's take a closer look at this framework. So we have the input images from multiple sources and a target. After a feature extractor, we can have the feature from either source or target. To achieve some discriminative feature for your final task, we will have this branch, which is trained on your source labeled data, and we encourage this branch to have very low loss for your desired task, like traffic counting. Simultaneously, in order to achieve the indiscriminative features from source and target, we develop this branch. This branch is domain classifier. We have a binary classifier between source I and target, and we encourage each classifier to have very high loss, which means the input source feature and target feature are very similar with each other. So this whole architecture is adversarially trained. Before this adversarial training, there will be low domain classification loss here, and it's very easy to distinguish between source and target feature. After adversarial training, this classifier has very high loss, which means the source and the target feature are mixed together, are aligned. So it's very hard to classify them. So this whole architecture are trained on the source labeled data and unlabeled target data. So this desired task branch only trained on the source data, and this domain discriminator are trained on both labeled source and unlabeled target. Such framework is also guaranteed by the theoretical study. We first propose this generalization bound on the target error like this, and then we want to minimize this generalization bound to get the bound minimization algorithm. So to minimize this bound, we connect between this divergence between multiple sources and target with the binary classification and formulate the objective to be a minimax optimization problem like this. And this optimization problem corresponds to this architecture design. So with this method, we can see that we achieve almost like the best performance on like the target camera compared with the baseline methods. As you can see here, given a target camera, we train on different number of sources. This visualization as a target camera trained with 2 labeled source camera. And you can see our method MDAN has the best estimation of the traffic counts over different frames compared with all these baseline methods. Interestingly, we also had an observation that if we increasing the number of the labeled source into the training data, it doesn't always help with your target performance. To be specific, we can see here, we have the target error with 2 source cameras to be 1.7, and then we have like a target error to be like around 1.2 with 3 source cameras. And when we increasing the amount of the labeled source cameras into the training data, the loss of the error on your target camera decreases. This makes sense because the deep neural network are hungry for the labeled data, and if you have more labeled data, you have more information, and the target can have better performance. However, if after a certain point and you keep increasing the amount of the labeled source cameras, the error on your target can increase as well, which means more labeled source cameras even hurt your performance on the target. Similarly, on another target camera, we have such observation. This is because when you already have a lot of source labeled cameras, and if you keep increasing the source camera that is different or very different from your target camera, like the highway camera is very different from this target downtown camera. If you keep increasing this like labeled data from your into your training data, it can even hurt the performance on the target downtown camera. So such observation inspire us to do the domain selection, which means we want to select the source data that are closer to your target data. Such selection can be in the training stage or in the inference stage. To be more specific, you can see that we have like several cameras with this camera ID and the images samples from each camera. And this number is the PAD, proxy A distance, which measures the distance between your source and target camera. The larger the value is, the more difference is like between the source and the target camera. So you do see that for a given camera, the distance between this camera and other source cameras can be different. Some cameras are very similar, some cameras can be very different from this target camera. So such observation also inspires us that we should select the source data that are closer to our target to be the training data. So how to fulfill this goal? Let me introduce our second work, Multisource Distillation domain adaptation. So the intuition is that we observe different sources may have different relationships with their target. And even within one source, even within this source, different samples from the source may also have different similarities from the target samples. So we want to take use of such different similarity and distill the source images that are closer to our target to fulfill the domain adaptation. So here is the overview of this multi-source distilling domain adaptation method. We first learn the discriminative representations of the target for each source adversarially, and then we select distilled samples for each source to fine-tune the source classifier, and in the end, we design a normal weighting strategy to combine the multiple predictions. So let me introduce in more details. For the first stage, we separately pre-train a feature extractor F and a classifier C using the corresponding training data for each source. And in the second stage, we map the target into the feature space of each source adversarially by minimizing the empirical Waterston distance. In the third stage, we select the source training samples that are closer to the target samples. And we fixing the feature extractor, then use the distilled source samples to fine-tune the source classifiers. In the last stage, we extract the features of each target image, and we obtain the source-specific prediction. And in the end, we combine the different predictions from each source classifier to obtain the final prediction. With this methods, we can achieve almost all this best performance in different settings compared with the baselines. We also observe that the source-only methods are lower bound or a lower bound performance, and on average, the source command domain adaptation performs better than the single-based domain adaptation. Like similarly, we can also see our method achieve the best performance compared with the baselines. For some visualization, we can see that before adaptation, the target features are not well aligned with the source feature. But after domain adaptation, the target feature become more dense and fits the source domain more tightly. You can see the blue feature and the red feature representing the source and target features to be closer with each other after the domain adaptation. And here are some visualization for the activation map for the images. After the domain adaptation, we can see that we have better attention on the discriminative regions of the object compared with this attention before adaptation. The attention is just on some background which has no information for your final prediction. Similarly, we can observe more grand cam visualization from these images, and we can see after adaptation, we have better focus on the discriminative regions of your objects. So till now, we have introduced two domain adaptation methods on multi-source domain adaptation. Next, I will introduce an improved method for domain adaptation because we observed that there are still limitations of the previous two domain adaptation methods. So the most existing domain adaptation methods often try to learn the invariant representations. However, they cannot learn the invariant optimal classifiers between the source and the target. And such invariant representation learning can have some error, especially when your source and target has different label distributions and different optimal classifier. For example, if your source data has 50% negative and 50% positive, and your target has 80% negative and 20% positive. If you just force the source and target to have the invariant representations, they may force some target negative to be predicted as positive samples. So there will be some large error, 30% error in this case. So considering the limitation of the invariant representation learning, which is used by most existing domain adaptation methods, we further propose this jointly learning invariant risk and representations model, the LEAR model. By jointly learning invariant representations and invariant optimal classifiers, we can have better and more accurate prediction on our target data. So such model is also supported by the theoretical study. In this work, we provide a finite sample generalization upper bound for semi-supervised domain adaptation. Such bound implies a natural and principled way for a better generalization to the target domain by learning invariant representations and optimal classifiers simultaneously. Such method is in sharp contrast to previous works where only invariant features are pursued. So this is the bound for our theoretical results. We can see that the first two terms of this bound are the convex compensation of the empirical errors on source and target. And the third term is the distance between source and target representations. And the fourth term is the distance between source and target optimal classifiers. With only a few labeled data from the target, we can better estimate the target optimal classifier to achieve a better generalization bound for the semi-supervised domain adaptation. So the key challenges of this bound minimization algorithm is how to minimize the third and fourth term of this bound. So we want to learn a feature transformation to simultaneously achieve the invariant representations and risks across domains to minimize the third and fourth term of this bound. So with this bound, we want to propose this bound minimization algorithm layer, which try to minimize each term of this bound. And let's take a closer look at how to minimizing the third and the fourth term. To achieve this goal, we would like to first provide the information theoretical interpretation of this generalization bound. So for the third term, which is to learn the invariant representations, in order to minimize the divergence between your source and target features, it equals to that the domain is independent with your representations Z, your feature Z, which is also indicating that the mutual information between the domain and your representations are minimized. And for the fourth term, which is trying to learn the invariant risks, it also indicates that the domain is independent with your final prediction given this representation Z, which is also indicating that we want to minimize the mutual information between the domain prediction and your representation Z. So the intrinsic objective becomes that we want to achieve the independence of the joint distribution over Y and Z across domains. In order to achieve this goal, we want to identify the causal features that best support the prediction and enable the same predictor to be optimal across domains, which equals to this one. And you can see that it is the jointly learning the invariant representations and invariant risks. D here indicates the domains, which is like the invariant or background of your images like snow or grass. And Y is the final prediction of the objects like bear. And Z is like the causal feature, like the shape on the contour of the bear, which best support the final prediction. So with this theoretical interpretation, to achieve the invariant representations, we use the adversarial training, similarly as the previous works, to learn the features that is indiscriminative between the source and target. To achieve the invariant risks, we want to decompose this mutual information into the the entropy between these two terms, and it can be they can be regarded as the empirical errors of two predictors. So we have the final loss function as this one, and design the framework as this figure shows here. We have a branch to learn the invariant representations and the branch to learn the invariant risks. With such a model, we can achieve almost best performance on all the settings and different data sets on image classification problems. Here, we studied that what is the target performance given different amounts of labeled target images. We can see that if you increase the labeled target images, the performance can on the target can be better and better. The interesting observation is that we can achieve even higher accuracy than the training with full target labeled data. This is very interesting because if you train a model with a fully labeled target data, you can achieve some performance 83.67. But if you use our method and you just use 25% labeled target data, you can achieve even higher accuracy, like around 85%. So this can save a lot of labels on your target data. So here we have some like visualization of the final prediction. You can see that with our model, we can have better attention on the contour, on the shape of the object. However, without like our method, the attention sometimes can be focused on the background, which doesn't give discriminative information for a final prediction. Besides the image classification task, we also work on the like traffic accounting task, which is essentially a regression problem. So we have like 4 cameras in different locations of the city, and you can see that over different time, the count of each frame is also different. We take this 398 camera as the target and the 3 other cameras as the source, and we transfer from the source into the target. You can see here with our model, we can also achieve like better performance consistently with different labeled percentage and compared with the baseline methods. Here are some visualization. We can see that we can have better estimation of the traffic accounting over different frames compared with the baseline methods. Cool. So till now, I have introduced the several models for domain adaptation. And actually, in the real world, the data can be long-tailed. For some classes, there can be very few annotations or even very few samples in the real world. So for the domain adaptation, the setting is that we have several cameras with the labeled data, and we have a target camera with non-labeled data. But the classes we want to recognize between the source and target are the same. For example, we both want to recognize the cars in the source and the target. However, in the real world, the classes of the objects can be long-tail distributed. We have a lot of classes that has many labeled data and samples. We can also have some classes that with very few samples. And we can even have some classes that has no samples in the training data at all. So you can see here, in the target domain, we can have some like unknown classes with very few labeled very few labeled data. Like the classes in the source data are the cars with a lot of labeled samples, but the class in this target can be trained, which is different from a source and which has very few labeled data. So such problem is even more challenging than the domain adaptation problem, and we define such problem to be cross-domain few-shot learning. To solve this problem, we would like to pre-train the model on the known classes from the source domain, which has a lot of training samples. And then we want to train and test on the novel classes from the target domain with very few training samples. The source domain can be the general domain because the general domain like ImageNet are the photos from the daily life, so they can have a lot of samples and it's easier to label them. But the target domain can be some images from the distant domain, like medical data. Such domain has fewer they have nice samples, and it is very hard to label such samples. We can observe that the source images and the target images are very different. The source are the daily life photos, and the target are medical photos. So they do not share the high-level patterns like the wings of the bird. However, they may share some middle-level patterns like the circle and the dots. Based on this observation, we would like to compose the novel samples by the known classes. we want to first reconstruct, do the reconstruction, because the knowledge that can be transferred from the known classes into the unknown classes with the high level semantic patterns, especially when the source and the target are not that different from each other. However, as I shown here, the target can be very different from a source, so they may not share the high-level patterns and they may only share the middle-level patterns. So there will be some residue term between the reconstructed feature and the original feature. So we want to predict these residue terms based on the middle-level features. So here is the general framework of these methods. So we can view the coming training sample as a pseudo unknown class sample, and we first conduct the high-level feature reconstruction based on the neighboring prototypes of that sample. Then we do the residue term. We calculate the residue term as the difference between the extracted feature and the high-level reconstructed feature. And then we use the middle-level features from the multiple middle layers to dynamically predict this residue term. So with such mechanism, we can see that we compose the novel samples from the unknown classes by the known classes features. And interestingly, we observe that if the targeted images are very different from our source images, we will use more middle layer features to reconstruct the target images. But if the target images are more similar with your source images, we will use more higher level layers to predict or to reconstruct your final target images. So this also corresponds to our intuition that if your target is very different from a source, we should explore more of the middle level features. With such mechanism, we can see that we achieve the best performance compared with the baseline methods, on the pencil domain. Pencil domain is this one. This is very different from your source images. And on this cells, which are medical images, we can also achieve better performance compared with the baseline methods. Similarly, for a domain which is closer to your source domain, it can also achieve better performance. So till now, I have introduced the domain adaptation and the few short cross-domain learning problem. Further, we can also say that actually there are some classes in the real world that has no samples in your training data at all, which means you only have a lot of source labeled data, but for the target domain, you do not have any samples at all. Such a problem is even more challenging, and such problem is defined as generalized zero-shot learning problem. So how to deal with such problem? Let's take this data as an example. So we have the classes from the known domain, which is a source domain, and we know the class label for this images, and we have the semantic feature the attributes for each image. Also, we have some image in the testing stage that doesn't appear in the training stage at all. So we can regard such a class as a zero-shot unseen class. The problem is how to take use of the features learned from the known classes and predict the class of the unknown images. So the biggest challenge for such problem is that you have no training data at all for such classes. So how to train the classifier to recognize the unknown class without training data at all? So there is a famous quote, "What I cannot create, I do not understand." So in order to understand these samples, we want to first generate these samples. So we would like to generate the features of these unknown classes based on these attributes description. And then based on the generated features, we can train the model with this features extracted from the real images and the features generated from the unknown classes. Then we can, after we train this classifier, we can try to recognize the unknown classes. So here are some dual adversarial semantic consistent network to generate these features from the unknown classes. So we have the images and as the input of the visual space. We also have the input of the attribute description for each class. So we based on the visual extracted features from the images to generate the semantic description. Similarly, based on the semantic description, the attributes, we generate the visual features. So this is like a dual generative model. And based on the generative feature, we can train the classifier to recognize the unknown classes. With such mechanism, we can also achieve better performance in most cases. And you can see that the generated feature are close to the ground truth feature. And with this generalized zero-shot learning mechanism, we can also solve the text classification problem in the medical domain. Actually, in the healthcare domain, it's really hard to obtain a lot of training samples. For example, this ICD coding problem, we want to classify each document of the which is the record of each patient into the coding of the disease. So here we have this document for a patient, and we try to classify this document into multiple ICD codes. Each code indicates one disease. However, there are several diseases, even more than 5,000 diseases, have very few training samples in the training data, and there are more than 50% diseases that has no training sample in the training data. So we want to solve this problem, which is also a generalized zero-shot learning problem. And similarly, we want to generate the feature for the disease that has no training data at all based on the label description as this one. And then we can also take use of the sibling codes. Even though we have no training data from this code, we may have some training data from its sibling code because the ICD coding has this hierarchical structure. So with the document from the sibling codes, we can extract the feature, and we encourage the feature from the sibling codes to be very close to the feature generated by this unknown code. So after we generate this feature, we can also fine-tune the classifier based on the generative feature and have some better prediction of the unknown code. And you can see here, we increase significantly compared with the baseline. The baseline method almost has a 0 F1 score, but we increase a lot with our method. And similarly, we can see that after our method, we can generate some feature that is close to the sibling feature. So till now, I have introduced a series of research on the domain adaptation, few-shot learning, and zero-shot learning. Actually, all these problems can be summarized as learning with limited labels. If we have unknown classes in the target with few-shot samples, the domain adaptation becomes the few-shot learning problem. If we have both domain shift and new category on the target, it becomes the few-shot cross-domain problem. And if we have no training samples at all, it becomes zero-shot learning problem. So in the future, we would like to explore the domain adaptation with active learning, and we would like to explore the online learning with auto-labeling and retraining. Here are some reference, which is support all the methods I introduced just now. And please feel free to contact me if you have more questions. Cool. So yeah, I guess this is the end of my talk.